Jeremy Weiss is going to be giving our presentation today, and he is the Climate and Geospatial Extension Scientist with the School of Natural Resources and the Environment at the University of Arizona. Jeremy has a PhD also from the University of Arizona in geoscience and a Master of Science from the University of New Mexico in Earth and Planetary Sciences. And he's got several publications relating to climate, including sea level rise and drought. And he has a lot of experience with climate data. I was very lucky to be able to see a presentation of his at New Mexico State University last year. And like I say, it's our great pleasure to have him here. And Jeremy, if you want to take it over, we are looking forward to your talk.
Great. Well, thanks, Ginny. And good morning to all the attendees. I thought it was a pretty neat opportunity to be able to facilitate this discussion this morning on climate projection data and some of the ins and outs of its applications, particularly so because I really haven't ventured too much into wildlife biology and management yet. So for me, this is kind of a new and exciting area in which to work. And again, happy to be here and facilitate this discussion. So this morning, I'd really like to touch upon a pretty wide range of topics, as the webinar advertisement noted, that are pertinent to working with climate projection data in applied contexts. I'd like to go over a couple topics, or a number of topics really, such as data availability, data selection. I'd like to discuss some of the details regarding climate change scenarios, as well as downscaling of global climate model output. I'd also like to cover some information regarding obtaining data and reformatting data. It's at times not a trivial task, as I'm sure many of you know. And I'd also like to touch upon sources of uncertainty when it comes to climate model projections, as well as confidence levels in projections of some important climatic phenomena in the region, such as El Nino Southern Oscillation and the North American monsoon. Today, I'd also like to do something a little bit different for a webinar, perhaps, or maybe different from the average webinar. And that is risking chaos breaking out effectively, in the sense that I'd like to have some interaction with the attendees during the webinar this morning. And to do that, we're going to be, if you look in your Adobe Connect interface, there's a chat function down in the lower right. Just make sure we're going to be using that for the interactive parts of, and a lot of the Q&A probably as well, perhaps. So just make sure that that setting is set to chat everyone. And with that, let's go ahead and try that out and work with this question that's on the current slide. What are some types of wildlife applications that have needed climate projection data with some of your experiences? And of course, since this is related to the Geospatial Advisory Committee, go ahead and note whether or not that was a geospatial application. So 15 to 30 seconds, go. Okay, we have multiple attendees typing. That's what my screen says. I'm sure yours does too. And we'll give it just a few more seconds to wrap up for those who want to put some input into the chat box there. Okay, well, let's move on to the next slide. And go ahead and keep typing if you're typing. Feel free to add something if it comes to you in the next few seconds as well. But in speaking with some of the Wildlife Society staff leading up to this webinar, some of the examples I was given in terms of where climate projection data were applied include wildlife distribution modeling, habitat modeling, and habitat use. We could see some of those showing up in the chat box, as well as something I hadn't thought of, which is more of a coastal environment instead of purely inland terrestrial environment. That last note or chat note there on refuge islands and impacts to coastal wetlands. So with those types of examples, it's pretty clear that a lot of us have a pretty well-defined need to use climate projection data. So let's go ahead and start digging into some of the details on that. The picture here kind of denotes something where I wouldn't be telling the truth if I didn't say that there weren't days when I felt like the gentleman here in the lower left of this picture. And that is to say that many of us have a lot of challenges, and you can alternatively think of them as opportunities to work with what has become a really enormous amount of climate data, in this particular case, climate projection data. And of course, what we want to do is, knowing that this data is out there, analyze it and channel it towards improving and informing wildlife biology, and in this context, wildlife biology and wildlife biology management. In other words, what we really want to do is take this information, all these climate projection data, which is really just a giant pile of it nowadays, really, and extract something meaningful out of it. And so in my case, what I found helpful is to kind of have a high-level workflow or data process that kind of steers me through thinking about the data and working with it in a pretty, hopefully, sound manner. Of course, that always starts with the applied research question or climate information need. Our interaction with the chat box a few minutes ago established some of these needs. And the first step for me in this case would be to ask, well, are the data available that I'm looking for in terms of an application? And in the case of a lot of, perhaps many of the wildlife applications, I'd hazard to guess that a lot of these data are available in many cases. So we really don't have to worry about developing our own data set, fortunately, as a climate projection data development is not a simple task. So fortunately, again, a lot of these data are already out there. And as we know, you can really find climate projection data in quite a large number of places and in a variety of forms. So many places, in fact, that I personally have trouble keeping up with them all. So what I have here are a couple different types, and I call one subset direct from the factory. And what I mean by that is that these data are direct from the climate modeling centers around the world. These are the output of the global climate models that are used directly by the IPCC, the Intergovernmental Panel on Climate Change, to inform their assessment reports that come out every 5, 6, 7 years. There's another subset that I've termed through middleman, and these include climate projection data that have been post-processed after these modeling centers have produced the data. And that could be, in the sense of downscaling these data or reformatting them to be able to bring them directly into a GIS software, for example. And I list a few examples of these data sources here. Again, far from being exhaustive. There are really a large number of places that supply climate projection data nowadays. That said, the next step in the data process, it brings us to selecting, okay, from which of these sources do we get the data from? And in order to do that, we really have to start comparing our needs with a lot of the different types of climate projection data that are out there, or climate projection data that really has a lot of facets to it. And some of these facets could include the which climate model intercomparison project, or CMIP, do we pay attention to? There are different mission scenarios that we can choose from. And again, something like downscaling, do we use the original direct from the factory data sets, or do we use a downscale product? So let's get ahead, take a look at some of these issues. And in the case of the CMIPs, projection data from the CMIP-5 simulations are the newest, the most recent set of coordinated climate model experiments. And these are the same ones that are evaluated in the 5th assessment report, or AR5 of the IPCC. And the initial steps in working with these can be kind of intimidating, as that quote on the left of the slide denotes. The number of models and the complexity of the CMIP-5 experimental design confronts us with what really might seem to be a pretty baffling collection of model output, and I would agree with that. So for instance, there are more than 20 modeling groups contributing to this, more than 50 models. There are 2 climate change experiment types. You have the long-term or century scale type, and the near-term or decadal predictions, experiments run on 10 to 30-year time windows. But that's not all. We also have a few different types of models that are part of the CMIP-5 ensemble. And the first one is the atmosphere-ocean global climate models. And those are the ones that were pretty typical in the CMIP-3 ensemble, which was used to inform the last assessment report of the IPCC in 2007. With these models, they're running both the near and long-term experiments, and they're driven by time-evolving concentrations of greenhouse gases. Those same aspects are shared by the Earth system models of intermediate complexity, which are really used, since they are kind of stripped down in a way, simplified. They are used for high volume runs and really lengthy runs as well, due to the computational requirements involved with running a climate model. And then lastly, we have something new to the AR5, which is the Earth system model. And these are run strictly on the long-term experiments. And since they have an integrated carbon cycle model in them, they're driven by time-evolving emissions of greenhouse gases, in contrast to the concentrations that the other 2 use. So they're given the emissions of the greenhouse gases, and then the carbon cycle model figures out what the atmospheric concentration, quote-unquote, should be. A few more quick notes on the CMIP-5 simulations. Their emission scenarios are based on something new this time, called the Representative Concentration Pathways, or RCPs. In contrast with the 2007 IPCC report, or the CMIP-3 ensemble, those were using the SRES, if you recognize that acronym, scenarios. So a different set of scenarios, A1, A2, B1, B2. You might be familiar with those. Similar, but not quite the same. Also with the CMIP-5 data sets, the models are more comprehensive, as we were just describing. They do have a higher spatial resolution this time around. There's improved metadata for the models and the experiments, so it's easier for people like us to access the data and understand what we're getting into. And there's also an expanded list of model output, more variables, different time frames, more time frames perhaps. And these are often in the net CDF or net common data form file, something we'll address later on. So there's a lot of advancement between the CMIP-3 and CMIP-5, as I've just described. And so I think it'd be a good chance to get some more input from the attendees right now. And in the sense of answering this question, in terms now, knowing this and knowing what, from your experience what you brought to this webinar, in terms of selecting the climate projection data for wildlife applications, should we be using CMIP-3 data or CMIP-5 data? Again, 15 to 30 seconds, well, even shorter than that perhaps. So go ahead and put those, what you think what your answers are in the chat box real quick, and we'll go from there. So go. Okay, a few more people are still typing. We'll let a couple more of those lines come in, and then we'll start to discuss them. Okay. CMIP 5, do the higher resolution, and I agree, higher resolution does allow us to get some of those extra details, especially in the dynamic models, which is good. Improve the realism of different phenomena. We have a good point there. Using the CMIP 5, but past studies have used CMIP 3. So again, since the scenarios aren't the same and the models aren't the same, it's tough to compare. So using the CMIP 3 as well for current applications is good for comparison. Let's dig into this a little more. The authors of one of the downscaled climate projection data sources that was listed on one of the first slides had this to say a couple years back, that even though the CMIP 5 is newer, it's not been determined to be a better, more reliable source of climate projections compared to the CMIP 3 climate projections. And that the CMIP 5 projections should be considered in addition to, and not a replacement of, the existing CMIP 3 projections, unless the climate science community comes up with a really good reason as to why CMIP 5 should be used in place of CMIP 3. And so, from those types of comments, recent comments from the climate science field, we would get the impression that any work done with the CMIP 3 projection data really hasn't passed its sell-by date. And I think one of the reasons why here is that those projection data, those projections of future global climate are still plausible scenarios. So what are scenarios? Let's get into that real quick. Well, we know that past trends, even though they're pretty valuable in providing evidence for preparing for and anticipating future environmental changes, by themselves, however, they're insufficient for assessing the risks associated with, as we know, what is an uncertain future. And in the context of future climate change, where is some of this uncertainty coming from? Some of it's coming from how we deal with or don't deal with current and future rates of emissions of greenhouse gases. Some of the uncertainty comes from a large variety, as we now know, of different global climate models. And some of it as well stems from some of our incomplete knowledge of the global climate system. We know a tremendous amount, there's no doubt about that, but there are still some things, obviously, we still are working on trying to really get a good handle on as far as knowing. So in order to deal with this uncertainty, that's where the value of scenarios come in. And even though they're not predicting future changes, they're nonetheless describing potential plausible future conditions in a manner that's going to hopefully support decision making under this broader condition of uncertainty that we just talked about. And so if we look at the RCPs from the CMIP 5 data sets, they have 4 different scenarios that the CMIP 5 data were experimenting with. And you can see these here in this particular figure, RCP 2.6, 4.5, 6, and 8.5. And what those numbers are referring to are the radiative forcing, which you can kind of think of as the extra heat added to the climate system due to additional greenhouse gas concentrations, or increasing higher greenhouse gas concentrations. And so, right, we have on the order with the RCP 8.5, That's typically thought of as the quote-unquote business as usual scenario, something where if we're not going to reduce greenhouse gas emissions, that is a plausible future under those types of conditions. And you can see there how the other three RCPs fall out in terms of reducing the amount of heat we add by reducing the amount of greenhouse gas concentrations, or at least the emissions thereof, in the atmosphere. So a couple other quick points about scenarios. One is that they're often used to develop and test decisions under a variety of plausible futures, and sometimes this variety includes a scenario that is high risk but low probability, as well as a low risk but high probability. And it's often argued that a scenario-based approach is going to strengthen an organization's ability to recognize, adapt to, and take advantage of, perhaps, in some cases, of the changes that are going to take place over time. Okay. Believe it or not, we're still in the data selected step. I'm thinking that you're thinking that it's not trivial, and you're absolutely right. That certainly has been my experience. So let's take a quick look at downscaling and move on to the next step. So the reason for downscaling, and two of the main methods there, statistical and dynamical, are listed, is to take the relatively coarse GCM output and generate projections of future climate change at finer spatial scales that are going to aid in climate change impact assessments. And we can see an example here in this slide where the figure in the lower left shows the output from a global climate model. It looks like the variable here, temperature. The red and orange colors denote warmer temperatures. Purple and blue denote the cooler temperatures. In the second figure, middle figure there, where it's zoomed into California, you can see how coarse the spatial resolution of these global models is. It's on the order of 150, 200 meters for a grid cell size. Now moving to the downscale GCM output, it's on the order of tens of miles as opposed to hundreds of miles. And we can start to see some of the features that we know exist and are important in terms of regional climate. For California, for example, we can see the Central Valley, the Sierra Nevada showing up here, some of the coastal mountain ranges, and even Death Valley over here on the eastern side of the state. So some quick notes on the statistical and dynamical downscaling. The statistical downscaling is going to really rely on the relationships that are based on observations. These relationships are between broad-scale atmospheric variables and the local ones. And some of the methods there include linear and nonlinear regression, analogs, and even weather generators. In terms of the dynamical models, they're using regional numerical climate models to resolve some of the fine-scale features that aren't represented well or even at all, as we just saw in that example of California, in the global climate models. So some of the strengths of statistical downscaling include that it's computationally inexpensive. You can produce data on finer spatial scales than the dynamically downscaled models. And it's also applicable to a really wide range of variables. With the dynamical models, one of its main strengths is that it's going to be representing some of the important dynamical processes that are not defined in statistical downscaling. For example, when it comes to the North American monsoon here in the Southwest, it's going to be resolving some of the diurnal cycle of precipitation, the midday formation of the storms over the higher terrain, for example. Aspects like that. Okay, another good spot for attendee input. And let's assume we have a wildlife application of climate projection data that requires projections of extreme temperatures, either high or low in this case. Again, with your experience and knowledge that you brought to the webinar today, and with some of the information we're going over now, would you select model output from the global climate models or the downscaled models? And if the latter, which one? So again, 15, 30 seconds. Go ahead. Okay, we have a vote, or at least some experience with some downscale data, resolution there playing a very important role, statistically downscaled data in particular. We have more people typing just yet. Give them a few more seconds, and then we'll discuss this a little bit more before moving on to the next topic. Okay, more statistically downscaled data. And again, yes, a very important point there. The ability to understand what you're working with is very key, and we'll definitely beat on that point continuously through the rest of the presentation, the webinar this morning, and some more statistically downscaled model experience there. Good question there on as far as how steep the learning curve is with the dynamical models, and that's a good question, and I don't think it's too steep. I think it's achievable, getting up that learning curve. Okay, we'll move on. And before we kind of get back to that answer, let's go over some of the weaknesses or limitations of these approaches. With the statistically downscaled data, there's an assumption that these cross-scale relationships we determined with the observational data hold through time, and you might be out on a limb at times with that assumption, let's say. And there's also some concern over whether or not the statistically downscaled data are handling the projections of extremes very well. Some of the limitations with dynamically downscaled data are, again, computationally expensive, and there are some additional uncertainties that come into play through, particular model bias. Maybe it's too wet, maybe it's too dry, for example, with convective precipitation, as well as scale mismatches between some of the dynamical processes in the regional model and the global climate model from which the dynamical model is driven. Let me go back just a second to make this last point, and that is, so it's really hard to say which data set to use for these wildlife biology applications, for example. And even more so because in the case of temperature, the global climate models actually do a pretty good job on a regional level. And so if we're just thinking about changes in mean or variance, some of that information could actually be extracted from the global climate model data. So again, there's not a clear answer here, and this really brings home the point of being an informed user of these data, knowing their strengths and their limitations. And that way, when you get to applying them, you're better able to interpret your own wildlife biology application results. Okay, we got through the arduous task of data selection, so now it's time to get the hands on the actual data. And there are some different ways to doing that. Of course, you can just directly download it. If you're just needing a few files that happen to be available. However, if you're needing to work on, and we gave a few examples of those sites again earlier on with those on the sources slide. But if you're looking to, or if you're needing climate projection data on daily, monthly, or annual time steps, so you're getting more into a time series climate data need, downloading those files, and especially if you're working with multiple variables, downloading those individual files is going to be a pretty time-consuming and I would say, mind-numbing task. And so there are some different ways that we can go about solving that issue, and some different approaches that exist for remotely subsetting and retrieving these data. One such approach is combining the use of OpenDAP, which is basically a protocol for network data access, with what are referred to as threads data servers. And I give an example there on the left side with some code from MATLAB software environment. Certainly, if you're working in an R environment or other environments for that matter, again, this isn't the only way to do this. Those types of coding solutions are applicable here. Alternatively, there are some web-based user interfaces that perform a similar function. And I give an example here that's targeted at some of the statistically downscaled data. Again, this data set was mentioned on a slide earlier on. Okay, let's go ahead and get to the next step, which is the data format issue. And I know, for example, leading up to this webinar, there's some discussion on GIS software applications and how do you get these data into a GIS software environment. So, of course, if they're available, terrific. We can just bring them in directly. However, if not, of course, we're going to have to worry about reformatting them and transforming these data. And there are different ways and challenges that are inherent here. And as probably many of you know, a lot of the climate projection data nowadays comes in various forms, as we're just noting. But NetCDF files are the most common, and there's some good reasons for that. Listed here, for example, NetCDF files, they have metadata associated with them, so you can know exactly what you're getting and how it's structured in the file. They can operate on various operating systems, ingestible by various operating systems, machine independence. They're really efficiently subsetted, and they can be appended as well. If you're working with this type of a file as model output, if you run your model again with an extra year of data, you can just append that onto the end. And I got another code example here on the left. Again, it's from a MATLAB software environment, not exclusive to MATLAB for sure. But that is one particular solution here as far as cracking open these NetCDF files, which sometimes isn't the easiest task, depending on how many variables are in them. In terms of bringing it into a GIS software environment, as I noted, there are a few sources of GIS-ready climate projection data, and I list two of them here that you're probably familiar with. But my impression is these GIS software-ready climate projection data are pretty limited. Limited in the aspects of, not all models, not all scenarios, perhaps not all variables, or at least the ones you need. Certainly not all years. Though it's not. Those aspects aren't always complete. Let's say with the GIS software-ready data. Some of you are familiar, probably, I'm sure, with the ArcGIS Multi-Dimension Tools Toolbox. That, of course, can be used to bring a NetCDF file into GIS software and display it. My experience has been that I really prefer to work in a different environment, especially when the NetCDF files get somewhat complex and large. Again, going into a MATLAB or an R environment to work with those NetCDF files. In my experience, I've also had some, tried some different approaches with bringing or trying to bridge GIS software with climate projection data. And I have one here depicted on the right in the figure, and that is to, if you're able to figure out the grid or raster mesh of the projection data, which I've done here, you're able to either take an area of interest. In this case, it was for a project with the Tohono O'odham Nation in south central Arizona. And having that mesh of the climate projection data, you can then, subset or figure out a subset of the climate projection data, kind of maybe working backwards in a sense, where you're either surrounding the area with a bounding box, which is the somewhat thicker black line around the nation boundaries there, or if you're trying to figure out a subset of climate projection data that are more based on the irregular polygon of interest. In this case, those would be the aqua-colored squares in this figure. Okay, so we have the data in hand. It's in the right format. Now it's time to work with it or go through some analysis. And for that, I'd like to cover a couple different things, including the concept of ensembles versus individual models. Which climate projection data do you use in that sense, as well as the representation of some of the important regional phenomenon. And I mentioned El Nino Southern Oscillation and the monsoon earlier. Certainly that is something we'll talk about here shortly. Okay, so whether to use an ensemble, or really an ensemble, what they mean there is just a comparable group of models or selected individual models. This has been a debate that's going on over the last few years, really, in climate science. And I don't think there's a real clear answer to that question. I think the short answer is it depends. But nonetheless, let's not get into the gory details. Those gory details, if you'd like to get into them, are a good place to start, at least, are the two references there at the bottom of the slide. And I'll list those references in full at the end of the webinar today. But just to hit upon a couple quick points regarding this issue. When it comes to ensembles, some of the strengths are that obviously it's going to provide a larger sample from which to draw climate scenario information. Some of its limitations are that it's not designed to systematically sample uncertainties. So oftentimes or at least some of the time, that's referred to as an opportunistic sample. If you think back to statistics class and getting a sample upon which to do statistical tests or figure out a distribution function or a histogram of the data, we're really not randomly selecting models to build that sample, which is, of course, one of the statistical requirements of such an activity. We don't have all possible models out there, and in fact, the models that we do have aren't necessarily independent from one another. Some of them share components. For example, models may share an ocean circulation component, or an atmospheric circulation component, or a land surface component. So, we violate that rule of independence, again, in the statistical concept or context. Also, as we were talking about earlier, a lot of different CMIP5 model types are out there and part of the ensemble. And so that may make it hard to interpret such things as a simple model average. When it comes to individual models, of course, one of its strengths, or the argument for this approach, is that you can select the models that are doing a good job of representing the key features of regional climate that you need to assess, some application of these data. The limitations there, of course, it's a smaller sample from which to generate climate scenario information. So we mentioned the key climatic features just now. Let's talk about them really quickly. For the sake of simplicity, we'll just focus on El Nino and the monsoon. Unfortunately, it still remains pretty challenging for people in the climate modeling and climate science business to model these things really, really well. A lot of really smart people are working on this, and fortunately, the realism of these phenomena and the skill of their model representation has been increasing as time goes by. That said, it's still not perfect. Nonetheless, based on the last assessment report by the IPCC in 2013, some statements were produced and supplied that let us know kind of where things are at when it comes to these particular phenomena. And there's high confidence that ENSO remains the dominant force, really, in interannual or year-to-year variability in the global climate. However, there's low confidence in future changes in its intensity and spatial pattern, not only how it develops and where it develops in the Pacific Ocean, but also with its teleconnections, the far-flung impacts that it has. In the case of the North American monsoon, one comment or one conclusion to be made is that it's likely that there will be an increased frequency of summer temperatures. On the precipitation side of the monsoon, however, there's low confidence in projecting or what the projections say about changes in precipitation. Quick note there is that the IPCC report, how they define the North American monsoon area was that they included South America and into Mexico up into central Mexico, so the quote-unquote core region of the monsoon. They didn't get into the northern periphery where we are, so it's not exactly, these statements don't exactly cover us here in the Southwest. Okay, so again, going back to this high-level workflow and what I find helpful for me in working with climate projection data, there's one more step there that I have with data visualization. I'm not going to go over that today, with your wildlife biology applications, certainly that step or a couple steps could be plugged in there in terms of working with some of the distribution models and habitat models, for example. At this point, and again, this isn't an exclusive list of steps, and you can mix and match and pull different things in. But as far as laying out the workflow in working with climate projection data, I think this is at least a good start. And hopefully by going through this, we've ended up at our applied research answer, and or in other words, a climate information have as opposed to a need. And we've done a good job with it, understanding the data, a good point that was brought up in the chat box earlier, and not only understanding the data better, but also then being better able to, as this slide says, interpret what it is we're working with and what it is the numbers are saying. And that, of course, makes us better able to interpret the application of these data in the wildlife biology context. Okay, so I'll wind things up, or wrap things up, rather, with just a quick note, a couple notes, really. The first is that, again, today's purpose was really to touch upon a number of pertinent subjects that I find have an important role to play when it comes to working and applying, or working with and applying climate projection data. And so I am happy, of course, I'm sure my contact information has been out there, either email or telephone, however you want to contact me, or if you're on campus, please feel free to stop by my office. And that is that I'm happy to go into all the gory details or much more detail on these different topics. So if you're working with a particular application and you're thinking about, say, individual model selection, which ones do well for the North American monsoon, we can discuss that and figure out the pros and cons as far as going with that individual model approach versus an ensemble approach, for example. The other point I'd like to make is that there are several climate and geospatial research groups here in the College of Agricultural and Life Sciences that are available. We're all located now in the new ENR2 building on the same floor, in fact. We're available for responding to various research and stakeholder needs, and I list here a handful of them of which I belong to. And so some are more focused on the geospatial aspect of things, and others are more focused on the climate aspect of things, and I'm kind of in between as it turns out. But needless to say, if you would like some more information on any of these groups, or all of them for that matter, just, again, contact me. We just kind of wrote up a quick informative flyer to let people know that we're here, and just a real brief description of what we do and how to contact us and who to contact. So, again, all of us are really more than happy to collaborate with the wildlife biology applications. Okay, here are those promised full list of references. And with that, we got, I believe, about 12 more minutes. So any questions, of course, I'm happy to answer right now. And another thing that you may want to do is, either via the speakerphone or the phone or the webinar audio or the chat box, plug in perhaps, this might be a parting question for you all, the issue regarding some of the regional climatic phenomena and how well we're modeling them and projecting them into the future. Think of some applications or experiences of yours where that information might be relevant in terms of how you're interpreting some of the wildlife biology applications and work that you're doing. With that, let's go ahead and answer any questions. Thanks, everybody, for attending. And again, please feel free to contact me if I can help out with more information.
Great. Well, thank you so much, Jeremy. That was fantastic. I've typed your email address into the chat box. And if anyone has questions, please either unmute your phone, I think that would be *6, or type into the chat box. And while we're waiting for any questions, you may have noticed you can download the PowerPoint. At the top, there's a file box in the right-hand corner of your screen, and you can download the slides so you have them for future use. Oh, looks like someone's typing.
Just one quick thing. I'd like to thank everybody for entertaining my forcing of an interactive webinar this morning and supplying some answers to those questions we were wrestling. So thank you. I thought that was more fun than the average webinar.
No, that was great, and thanks to everyone for attending today. And it looks like Bill has a question coming up.
Yeah, I'm coming. All right, here we go.
Or you can just, here we go. Jeremy, can you see that one?
Yes. The question is, with the amount of uncertainty in climate modeling overall, how can it possibly be useful to on-the-ground manager, to the on-the-ground manager? Good question. And of course, in a better, optimal, perfect world, we'd like to reduce that uncertainty as much as possible, or even get rid of it. Of course, we just can't do that for a number of reasons. Some of them technical, some of them based on future human behavior, which I certainly wouldn't try to predict. To be honest with you, very difficult to do that. So I think there I'm going to answer by pointing back to the scenarios concept and the utility there as far as if you have a range of uncertainty. In the case of temperatures, it might be a range of future temperatures at a certain decade in the future being between, say, 2 degrees Fahrenheit warmer and 8 degrees Fahrenheit warmer. Again, this is just a hypothetical example. I think with scenarios, where they lend their value is to be able to pick 2, 3 future scenarios, and those can be developed. It's not just the scenarios that the IPCC is using and handing down with these data sets. It's individual groups, and I know Greg Garfin, for example, has a lot of experience in this, and he was one of the ones listed on that previous slide of the climate and geospatial groups, where they work with kind of these sector-specific or particular groups of on-the-ground managers where they develop their own scenarios for future climate and that are tied into what's important to the issue at hand. So if, for example, in our riparian areas, there may be different scenarios for future stream flow. If you're thinking about any forest applications, maybe there are different scenarios regarding the frequency and intensity of future drought. In any case, what the scenarios are trying to do is provide, instead of just a myriad of potential futures, which is what you get out of the climate data effectively, they're just going to give you a small number, a handful at most, that you can use to test your system in a sense, or to see, plug them into your management system and the biological system that you're working in, and see if you're crossing any important thresholds, so to speak. Are any critical environmental conditions being passed under such scenarios? And I think that's where the value of that approach comes in, is that you can test your system to potential futures, not all, but just a few, and you can dial that into your system as well to make it most relevant. And hopefully through that manner, and it's kind of an iterative manner, of course, as time goes by, but hopefully going through that exercise is going to help you anticipate future decision points or important thresholds to your system. And having some degree of anticipation then may allow you to make decisions to either take advantage of or prepare for such thresholds being crossed, for example. I hope that helped.
Thank you, Jeremy. Well, I had a question, and I was just wondering, you mentioned the differences between statistically downscaled and dynamically downscaled data, and I was wondering if you had any recommendations on when it might be better to use the dynamically downscaled data. As I mentioned, I've only ever used the statistically downscaled data. Several people, that participated, it seems like that's kind of what we have greater experience with. So if there's particular instances in which the dynamically downscaled data might be more useful, that would be great if you have any thoughts on that.
Sure, and in fact my experience is such that I've worked much more with statistically downscaled data as well. The dynamically downscaled data, it can be limiting in the sense of not all models being dynamically downscaled. And I think that's somewhat a function, or maybe even largely a function, of just the fact that it is so computationally expensive they can't do everything and downscale everything dynamically. That said, again, it's there's the general thought of weighing the pros and cons, some of which we went over during the webinar today. Dynamically downscaled data, some of the value I think there in terms of working in the Southwest might be with the representation of the North American monsoon. And in fact, there's a group here in the atmospheric sciences, some of you may know Chris Castro, who's done a lot of work with dynamically downscaling the global climate model data, projection data, for the Southwest, and taking a better look at the monsoon and seeing how well these dynamical models do with representing some of those aspects of the monsoon that aren't in the global climate models. I mentioned the diurnal cycle of convective precipitation development earlier on. There are some global climate models that do better at representing the North American monsoon, and those are the ones that he's working with in terms of dynamically downscaling them. So there's some value there, and again, that gets to the ensemble individual model issue also that we talked about today. So if your wildlife application, going back to Bill's question and my comments there, if your wildlife application is really hinges on summer precipitation, then thinking about using some of these dynamically downscaled data that are based on global climate models that do a better job at representing the North American monsoon, going that route might be a little more warranted in applications such as that.
Okay, great. And are those data sets that you mentioned that Chris Castro is working on, are those going to be made publicly available, or are they already available?
I think some of those data are available, and I'm not sure if the latest work that he's done is quite out there yet. That said, again, we can line up some of the global models that do a better job with the monsoon, and go through some of the other dynamically downscaled data sets that are out there and see if some of those models are available. And I think they are, certainly for the CMIP3 climate projections, possibly as well for CMIP5. I did not list any of those sources early on in the webinar today, but they do exist. And again, feel free to contact me if I could help out in any way in terms of finding those different sources and figuring out, okay, where are they, and also are the data that are say more applicable for monsoon projections, are those out there and available? So again, feel free to contact me, and I'd be glad to help out on that.
Great. Well, thank you so much. Barring any other questions that folks have, we are coming up, or we're at the 11 o'clock hour. So, Jeremy, thank you so much for your presentation. That was really great. Thanks to Melissa Merrick for getting in touch with you and getting this all set up. Thanks to everyone who called in today. And we will be making a recording of the webinar available. We'll be sending that out to the same email list that we sent out to before, so you can take a look for that. And thanks to New Mexico View and the Center for Applied Spatial Ecology down at NMSU for hosting the webinar with Adobe Connect. And unless there's anything else, it looks like most people are just saying thank you through the chat box. So again, Jeremy, thank you so much.
You bet. You're welcome. And again, thanks for the opportunity. And as I said earlier, it was fun to venture into wildlife biology applications today in a way.
Great. Well, thank you. We appreciate it.
Yep. Thank you, everybody.